As a heating and cooling professional, you work hard at what you do and take pride in getting the job done right. That's why we're here to talk today about measuring airflow for residential air conditioners and heat pumps.
We're not selling anything and we don't represent anyone's products or services, but as independent energy efficiency researchers, we've had the opportunity to make measurements on hundreds of residential systems, and we'd like to share that experience with you.
In this video, we'll talk about why proper airflow is important, how it affects system efficiency here in the upper Midwest, and we'll go through the pros and cons of different ways to measure airflow.
All right, let's get started.
Great.
Okay, here we are looking at a nice new high efficiency gas furnace that also serves as the air handler for a 2.5-ton central air conditioner. The question is, in the summer, is this furnace producing the right amount of airflow for the cooling system? We'll find out in a minute when we actually test it. But first, let's talk about how much airflow we're looking for and the consequences of not having the right amount. So you probably already know that manufacturers are generally looking for somewhere in the range of 300 to 400 cubic feet per minute per ton of cooling capacity in terms of cooling airflow. So here we'd be looking for something in the 800 to 1,000 CFM range. And I'm sure you already know the consequences of having airflow that's too low. You're looking at very cold evaporator coil temperatures and potentially a frozen coil and all the problems that go along with that. But when we test systems here in the upper Midwest, what we actually find is that we're much more likely to find airflow that's too high. And that's probably because here where it's cold, we tend to install big furnaces with big blower motors and we pair them up with small air conditioners. And that's bad too because high airflow creates its own set of problems. Number one, it hurts the ability of the system to dehumidify the air, and it also means a lot more blower electricity going through the system. And it just makes for a noisier overall experience and less comfortable overall experience for the homeowner. So we typically find that about half of systems that we test in our research in this part of the country have airflow that's higher than 400 CFM per ton, but only about 1 in 10 have airflow that's below 300 CFM per ton. When we correct those airflow problems, we typically see an improvement in efficiency performance of about 5%, but we've seen increases as much as 30% when airflow is really a long ways off. All right, so we're going to take a look and see how well this system is doing in terms of airflow by measuring it with a number of different methods. There are lots of different ways to go about measuring airflow. Here we're going to concentrate on just a few. We'll talk about using a calibrated flow plate. We'll look at airflow by measuring velocity in the ducts. We will look at static pressure and how we can use that with manufacturer's literature to estimate airflow. We'll talk about adding up airflow by measuring flow from individual registers. And finally, we'll look at the temperature split method for measuring airflow. Let's get started.
Let's start with this device, which is a calibrated flow plate that takes the place of the filter. Basically, airflow is very predictably correlated with the pressure drop across this plate. So just by measuring the pressure drop, we can get a good measurement of the total airflow going through the system. We really like this device and we use it often in our research. It's accurate and relatively easy to use. In the kit, you get basically 2 flow plates, different sizes, with a bunch of spacers that allow you to adapt the particular plate to any filter slot size. The main downside is the upfront cost, which is about $800, not including a good digital manometer, which would be a digital, or another way to say it is a pressure gauge. The one we have is made by the same manufacturer as the flow plate. It is right here that we'll be using. So it can do the pressure to airflow translation for us and give us a direct reading of airflow. We combine the flow plate with a pressure gauge. We can read CFM, cubic feet per minute, directly. So let's take a look at it in action. Okay, I'm going to drill the hole for the supply pressure reference tab for the true flow plate. This allows me to understand the supply pressure at this point with the filter in place and with the true flow plate in place, which by measuring that pressure, I can see the difference in resistance between the filter and the pressure plate. Helps me calibrate the airflow in CFM. I'll stick the static pressure probe in, point it towards the airstream. So now that the pressure tap is in place in my supply trunk line, I've turned the air handler on. We've turned it into cooling mode to get cooling speed. My digital manometer is reading static pressure in the supply trunk with the filter in place. I'm going to hit enter so that my digital manometer records that pressure. Next, I'm going to remove the filter and insert the TrueFlow pressure plate. So now that I have the TrueFlow plate installed, and I've covered up the filter slot opening just to eliminate any leakage that might occur there. Now I hook the TrueFlow plate up to my digital manometer. My digital manometer is set to read the particular flow plate. It's been programmed with the appropriate flow plate. We hook up the pressure hoses on either side of the pressure plate to the digital manometer, and the manometer is going to read out cubic feet per minute, CFM, of airflow through across that pressure flow plate. Right now we are reading 790, 790, 800 CFM I have here. So that's right on the low end that we were asking for this 2.5 ton air conditioning system. That's it. It's very simple, easy to use, and as we stated earlier, very accurate.
Okay, so our second way of measuring airflow involves measuring the velocity of the air in the ductwork. If we know the velocity of the air that's going through a section of duct in, say, feet per minute, and we know its cross-sectional area in square feet, we can put those two pieces of information together and calculate cubic feet per minute. Now, there's a couple of different ways that you can go about getting at this velocity. One is to use a pitot tube like this one, where you have a short tube with a hole in the end that you face into the airstream, and the greater the velocity, the greater the pressure on that hole, and by measuring that pressure, you can translate pressure into velocity. But today, we're going to use a different device, and that is this hot wire anemometer. Now this thing works by having a very tiny little wire in its tip that's heated, and as the air goes across that heated wire, it's cooled, and by measuring that cooling effect, we can translate into air velocity. Now it would be great with either the pitot tube or this anemometer if we could just stick this into the ductwork in any given spot, take one reading and be done with it. But the problem is that air velocity varies on the inside of the duct from one side to the other and from front to back, and sometimes it varies a lot. So if we really care about getting a good measurement of airflow, we're really going to need to make a number of measurements to get the average velocity of the air through that section of duct. So, okay, so here we are on the back side of the furnace, and I've marked the location of 5 holes that I'm going to drill in this nice long straight section of return duct. And those holes are not exactly in the same place. We won't go into today why they are where they are, but you can look that up online for more detail. But we're just going to go ahead and drill 5 holes, and then we'll run our hot wire anemometer through each one of them. Okay, so I've drilled my 5 holes, and now what I'm going to do is take this probe and I'm going to extend it all the way into each one of the holes and then slowly withdraw it while we're using our anemometer here to average the velocity across each one of those holes. All right, last hole. So we've done our 5 traverses through the 5 holes, and we've got our overall average velocity of 540 feet per minute. And when you multiply that by the size of the ductwork, which is 10 inches by 23 inches, that works out to just about 860 CFM. But I can tell you that we saw everything from 190 feet per minute worth of velocity there to over 800 feet per minute. And one thing we can show you is, because this little unit can data log and we recorded those traverses, we'll show you a graph of what those 5 velocity traverses look like. So another way to measure airflow is to take some static pressure measurements at different places in the system, and then take that information to the manufacturer's literature, where we can look up airflow as a function of static pressure. And we've really got 2 choices here. One is this static pressure rise across the air handler itself, and the other one would be the static pressure drop across the evaporator coil. In this case, we're going to use the rise across this furnace unit where we have the literature available, and you can see that we've put a static pressure probe down here in the blower return cabinet, and then we have another one up here in between the furnace outlet and the bottom of the evaporator coil. And we have the system running, and you can see that we're measuring just a little under ½ an inch of water column across this system. So with the manufacturer literature in hand, we can look up, based on the speed tap, the model of the furnace, and the static pressure rise that we're seeing, and we read off of the chart that we are seeing about 975 CFM, which is just a little bit higher than we measured with the flow plate, but in the same ballpark. Now, this method will work well if you have the manufacturer's literature. It won't work at all if you don't have that available. And generally, it's probably preferable, if you have a choice, to make the measurement using the total external static of the furnace rather than the pressure drop across the coil. Because with the coil, you can have issues with, is the coil wet, is the coil dry, and if that coil's been in place for a while, it may have some dirt buildup on it, and that could affect the readings that you get.
Okay, another way to measure airflow is at each of the registers using our hot wire anemometer. The hot wire anemometer measures feet per minute. If we know the register size and its net free area in square inches, so that it'll require going to the manufacturer's specification sheet to make sure we know the open area of the face of this grill. The hot wire anemometer measures feet per minute, and we have to do a traverse across that register to get an average feet per minute. Then we multiply that by the square feet opening of the register, and we then are able to calculate cubic feet per minute. So I'll start our traverse across this register, and we'll take several passes. Now, measuring airflow like this is great for diagnosing comfort problems and distribution issues, but we don't generally recommend it for getting at system airflow back at the air handler. It just takes too long to measure all of the registers in the home, and there's too much uncertainty from adding up all those individual register measurements. Maybe you're wondering how accurate these methods are, and we were too. So we made one extra measurement on this system using a calibrated fan to match the system pressure and give us a very accurate measurement of system flow. Compared to that gold standard, the other measurements are in reasonable agreement. The flow plate measurement was a bit lower and the measurement based on static pressure was a bit higher, but they were all within 10%. We didn't try to measure system flow from register measurements because it would have taken too long, and the temperature split method is just an indicator of flow, not a direct measurement. Plus, we couldn't do that test because the indoor conditions weren't right. Generally, we favor the flow plate test because it takes a quick and reasonable accurate value. The hot wire anemometer approach can be accurate, but it takes more time. The static pressure approach is the quickest, but we've found that the readings can vary some depending on where you measure the static pressure. And you have to have an airflow chart for that equipment you're measuring. But our test on this particular system showed that if you take your time to do it right, you can get good airflow measurements using a number of different techniques. One other note, if you're way above sea level, you might need to make adjustments for air density at altitude.
One final method for assessing cooling airflow is a really easy one to do, but you can only do it under certain conditions. And it's called the temperature split method. And it's a lot like measuring temperature rise when you're assessing airflow for heating, in that we're looking at the difference between the warm air, return air that's coming back to the system and the cool supply air that's coming out the backside of the evaporator coil. That temperature difference is called the temperature split. So if we have a system that's running really high airflow, that air is going over that evaporator coil very quickly and it's not getting cooled down very much, so this temperature difference or this temperature split will be on the low side. On the other hand, if we have a system with very low airflow, that air is dwelling on that evaporator coil for a long time, it's getting cooled down a lot, so we will see a large difference between the supply or the return air and the supply air that's coming out. And by gauging the magnitude of that temperature split, we can get a sense of whether our airflow is in the right ballpark. But there is a rub. Only part of the energy that's going into this cooling coil is going to actually cool the temperature of the air. The rest of it is going to removing humidity from the air, and it doesn't reduce the temperature. So depending on how humid the air is that's coming into the system, it will affect the target temperature split that we're looking for. If we have very dry air that's coming in, we'll be looking for a very high temperature split for our target. On the other hand, if we have really humid air that's coming back on the return side, we'll be looking for a relatively low temperature split. So to make this measurement, all we really need to do is measure the temperature on the supply side. Remember, measure the temperature and the dry bulb temperature and the wet bulb temperature on the return side, and then use our target temperature split table to look up based on return dry bulb temperature and return wet bulb temperature what our target number is, and then compare that to what we actually measure. But there's one other thing that we have to worry about. If we see a low temperature split, it could be that airflow is high, but it could also be something else that's wrong with the system. For example, if refrigerant charge is low, our system will not be putting out its full amount of cooling. That in and of itself will lead to a low temperature split, and if we're not careful, we could misdiagnose that as an airflow problem instead of what is really a refrigerant problem. On the other hand, if we see a high temperature split, then that's a pretty good indication that we have low airflow on our system. Now, the final consideration is that our temperature split target table only works for a certain range of dry bulb and wet bulb return temperatures, and if we're outside of that range, we're not going to be able to make that measurement. And that's the case here today. We're off the charts as far as being able to get a target temperature split, so we won't be able to measure it today. Well, there you have it. Some of the ins and outs of various ways to measure airflow. I hope this inspires you to start measuring airflow on the systems that you install or service.
If you found this video useful, please watch our other videos related to details of our research findings and tips for homeowners. Thanks for watching.